Hello and welcome. Mr. Johnson here, and in this video we're going to be talking about wavelength, frequency, and energy, how they're interrelated to each other, and even take a look at some practice problems. So let's go on and get started. So the first thing that we need to discuss is this idea of wavelength, symbolized by the Greek letter lambda, which looks like a fancy upside down Y. And wavelength is defined as the distance between two identical points on adjacent waves. So in other words, from crest to crest or from trough to trough. You've probably seen a depiction like this in your textbook where it shows wavelength being measured from peak to peak or crest to crest. You could also measure from trough to trough or valley to valley. But the reality of this is that I can take any two identical points on this depiction between the adjacent waves. So for example, I could pick a point here and then an identical point on the adjacent wave, and I could just as easily measure wavelength between those 2 points. And what we're going to find is that it's the exact same length if I've got a stable wave as what I would get if I measured from peak to peak or from trough to trough. Because if I take those 2 points at the peaks and I move them down, they're going to stay in equal distance, and therefore, regardless of what 2 points I pick on a wave, as long as they're identical points between two adjacent waves, I'm going to get the same length between them. But the easiest thing to do is to measure from peak to peak, and that's why most textbooks are going to show you that wavelength is peak to peak or crest to crest or from valley to valley, trough to trough. Okay? Lots of different terminology that can be used. But any way that you slice it, wavelength is a length. It's a distance, which means we have to use some unit of measurement of distance for when we measure it. So typically, we're going to do wavelength in terms of nanometers. And we've got a conversion that says 1 nanometer equals 1 times 10 to the negative 9th meters. In other words, 1 nanometer is 1 billionth of a meter. So it takes 1 billion nanometers to get you 1 meter. Right? Now, that conversion is going to be important because later on, when we go to do the math problems with this, turns out that even though we record wavelength in terms of nanometers, when we use wavelength in calculations, it has to be done in terms of meters. So we're going to end up needing that conversion factor a little bit further on down the road. So that's wavelength. The next concept is frequency. That's symbolized by this Greek letter nu. It looks like a fancy V. And this is defined as the number of wave peaks that pass a given point in a specified amount of time. Usually, we're going to define that in terms of seconds. So as a result, frequency is expressed in terms of hertz, symbolized with the units of Hz, or in terms of waves per second. So let's look at 2 examples. In this first one, you can see time 0 to time 1 second to time 2 seconds. So if I trace this out, starting at time 0, we see that I get 1 complete wave in 1 second, a second complete wave in 2 seconds. So we've got 2 waves per 2 seconds, which is going to simplify down to 1 wave per 1 second. That's our units for frequency. Another way that you'll hear frequency defined is the number of wave peaks that pass a given point. So again, we can look at from time 0 to time 1 second, and along that time period, there's only 1 peak. So any way that you do this, what you're going to find is 1 wave per second or a frequency of 1 hertz. If I take a look at a second example, we can do the exact same thing. We can trace it out over the course of 2 seconds, and if you count up the number of waves, you can see it trace 1 wave, and then 2 waves, 3 waves. Going on through, we're going to end up with a total of 6 waves over 2 seconds. So 6 waves divided by 2 seconds gives you 3 waves per second, or a frequency of 3 hertz. Just as easily, count the number of wave peaks that occur per second, and you can see there's 1, 2, 3 wave peaks. So hence a frequency of 3 waves per second, or 3 hertz. So that's frequency. So now how do wavelength and frequency tie together? Well, the relationship between it is one that is extremely important within the concept of chemistry as well as within physics. So here's 3 depictions. In this first one, the red one, you can see that over the course of 1 second that I can trace out 1 complete wave, 2 complete waves, 3 complete waves, 4 complete waves. So 4 waves per second, or sometimes you'll see it as cycles per second, for a frequency of 4 hertz. Now when I go to the green wave, take a look. What I'm doing is I'm halving that distance. You'll notice that for every 1 of the red waves, I can fit 2 of the greens. So what we notice is that when I half the wavelength, I end up doubling that frequency, and that's extremely important. Furthermore, if we go from the green to the blue, you can see again, I half that wavelength and I end up doubling the frequency. I get 16 hertz within that 1 second, or 16 cycles. So here's the relationship. If you have a long wavelength, you're going to have a low frequency. Conversely, if you have a short wavelength, you're going to have a high frequency. So, conclusion to this, as wavelength decreases, your frequency is going to increase. And as wavelength increases, your frequency is going to decrease. And as I pointed out, it's a direct inverse relationship. If I double one of them, I'm going to half the other. And again, we can see that. Here I go from 4 cycles per second, half the wavelength, and now I get double, or 8 wavelengths per second, or 8 cycles per second. So again, green to blue, I half the wavelength, I again double that frequency. So what this means is that the product of wavelength times frequency, lambda times nu, is a constant. And that constant, that's the speed of light, always. So what we end up getting is that the equation for the speed of light is lambda nu equals c. And we use the symbol of c for speed of light because it stands for the Latin word celeritas, which means swiftness. So that's why speed of light is a c, in case you've ever wondered. And because the speed of light, quote unquote, never changes, it's considered to be a constant with the value of 3.00 times 10 to the 8th meters per second, or more precisely 2.9979 times 10 to the 8th meters per second. But for our purposes in this video, I want to make the math easy for you. So we're going to just use 3.0 times 10 to the 8th meters per second. Want to also mention that you can see speed of light done in miles per hour, feet per second, kilometers per hour, kilometers per second, any type of distance per time unit, speed of light can be represented in it. But we're going to stick with meters per second. Again, that's going to make the math a whole lot easier when we get to it. So here's what we get. If lambda nu equals c, and c always equals this 3.0 times 10 to the 8th meters per second, then lambda nu always has to equal 3.0 times 10 to the 8th meters per second. And we can rearrange this equation depending on what we want to solve for. For example, if we are given wavelength and we want to solve for frequency, we can rearrange it by dividing both sides by frequency. If we're given frequency and asked for wavelength, then we can solve for wavelength by dividing both sides again to get what we're solving for on its own. So in other words, it can be rearranged, get rearranged for wavelength, where we're going to end up that lambda equals celeritas divided by nu, or speed of light divided by frequency. Or if we're solving for frequency, we're going to get that nu equals celeritas divided by lambda, or speed of light divided by wavelength. So now that we've got these two rearrangements of the speed of light equation, let's go on and look at some practice problems. So the first one that we're going to look at asks us, calculate the frequency of light that has a wavelength of 630.0 nanometers. So in these problems, as you probably know if you've seen any of my other videos where I work math, we're always going to go through and label out what we've got. So it's telling me to calculate frequency. That's what I'm trying to find. So nu is my unknown. And it tells me that it has a wavelength of 630.0 nanometers. So lambda equals 630.0 nanometers. And as I mentioned earlier, because Celeritas is done in terms of meters per second, our wavelength has to be converted over to meters. And that's where this conversion factor comes in, that there is 1 meter for every 1 times 10 to the 9th nanometers. In other words, 1 billion nanometers for every 1 meter. And when you solve this out, you'll get 6.300 times 10 to the negative 7 meters. So now I have my wavelength in terms of meters. I can go back to my standard equation of lambda nu equals Celeritas. And because I'm solving for that frequency of nu, I'm going to need to divide both sides by lambda, so that lambda cancels out from the left-hand side of the equation, leaving frequency by itself, and frequency equals lambda nu, just like what I showed you on the previous screen. And now I can substitute in values, knowing that the value of C is going to be 3.00 times 10 to the 8th meters per second. My wavelength in terms of meters is 6.300 times 10 to the negative 7th meters. Unit-wise, notice that meters in the numerator cancel meters in the denominator, and that's going to give us 1 per second, or waves per second, which are the units for frequency that we want. And when you plug this into your calculator, you should end up coming out with the value of 4.762 times 10 to the 14th. And just a quick reminder that many calculators, instead of giving times 10, they will denote it as E14, where that E means exponent of 10 of whatever value you've got, in this case 14. And then the units, as I said, when we look at these units, we're going to get 1 per second, but that's technically 1 wave per second. So we can record this as 4.762 times 10 to the 14th hertz. Okay? So that's if we are given wavelength and asked to solve for frequency. So the next question, let's start with frequency and find wavelength. And again, going through, calculate the wavelength. That's my unknown. For a beam of light that has a frequency of, here I've got a frequency of 7.56 times 10 to the 15 hertz. Again, I know that lambda nu equals Celeritas. I'm solving for wavelength, so in this case, I will need to divide both sides by frequency, so it cancels out from the left-hand side, and I get that wavelength would equal Celeritas divided by nu. And what's nice about this is I don't have to do any converting to get correct units, okay? Because I'm already starting out in hertz, and it's going to allow me to cancel directly. So Celeritas, again, is that value of 3.00 times 10 to the 8th meters per second. My frequency is 7.56 times 10 to the 15th hertz. And when I do this math, my calculator, I get 3.97 times 10 to the negative 8th. And now let's take a little look at the units themselves, because this is where some students get kind of mixed up. I have meters per second being divided by hertz, and it doesn't look like anything cancels. But if we remember that hertz really means waves per second, or 1 wave per second, then I've got units of meters per second divided by 1 per second. And hopefully you've learned in math that if you have a fraction divided by a fraction, then you can multiply the numerator, in this case meters per second, by the reciprocal of the denominator, which would be seconds per one. The units of seconds cancel. That gives me meters per one, or simply units of meters, which is what we would expect for wavelength. Now, if the problem asked for this wavelength in terms of nanometers, we would need to then convert those meters back over into nanometers. But that is how you work the wavelength frequency problems involving the speed of light. Again, when I work through these, please feel free to pause the video, work them out on your own first, and then unpause and check your work to make sure that you're doing it correctly. Okay. So that is wavelength frequency, speed of light. So now then, where does energy come in? Well, energy is related to frequency, and obviously, as we just saw, frequency is related to wavelength. But typically, we don't talk about an energy wavelength relationship. We talk about a frequency energy relationship. Okay, and I'll explain why in just a moment. But looking back at this diagram again, or this image of the three different wavelengths, here's what I want you to think about. If I've got a long wavelength beam of light, then there's not a lot of energy to it. And if I want to shorten that wavelength, I have to move my hand much faster. And if I'm moving my hand much faster to represent that wave, I'm having to exert more energy. So the idea becomes this, that if you've got a long wavelength, low frequency wave, that relates to low energy. Conversely, if I have a short wavelength, high frequency wave, that's going to relate to high energy. So what we get is this idea of the higher the frequency, the higher the energy. And this comes from this guy, Max Planck. He was attempting to explain this thing called the photoelectric effect, where you take a really intense beam of light, shine it on a piece of metal, and you eject electrons from that piece of metal. And what Max Planck realized or proposed is that there is a relationship between the quantum, or the amount of energy, and the frequency of the radiation or light that he was using. And he ends up developing this equation, E equals h nu, where E is going to be the energy of the quantum of radiation, in other words, the amount of energy, and we measure that in terms of joules. Nu is still frequency, that is meters per second or hertz, and then h is what we now know as Planck's constant, and it's defined as 6.626 times 10 to the negative 34th joule seconds. And a lot of times you'll see in textbooks J and then a dot S, or the little asterisk, where that asterisk means times. Okay, you typically can also see this as just JS, but a lot of people confuse that for them trying to pluralize the J. Okay, there's not an apostrophe there. You're not pluralizing. Okay, it's joule seconds. So how do we work these problems now? Well, let's go on and take a look and jump right into it. So this is asking what amount of energy is associated with a beam of light that has a frequency of 4.759 times 10 to the 14th hertz. So again, going through, what amount of energy? Energy is our question. Has a frequency of 4.759 times 10 to the 14th hertz. So that is my value of nu, 4.759 times 10 to the 14 hertz. And we've got the equation that E equals h nu. So there's no rearrangement that needs to be done. So what I get is energy equals Planck's constant, 6.626 times 10 to the negative 34th joule seconds, all times my frequency of 4.759 times 10 to the 14th hertz. We'll look again at units in just a moment. And when I put this into the calculator, what I get is 3.153 times 10 to the negative 19. And we've already talked about the fact that the units of energy should be joules, but I want to take a look at how that actually works out in this problem, because seeing joule seconds times hertz doesn't really give the idea of joules. until again you realize that hertz is 1 per second. So I have joule seconds times 1 per second. So as a result, seconds in my numerator cancel seconds in the denominator, and I'm left with joules times 1, or simply joules for the units of energy. Okay? So if ever you're asked to derive the units, this is the process that you would take. So that's the most straightforward working of Planck's constant equation for energy. But we can do another rearrangement, because if energy equals h nu, and as we saw previously, nu equals c per lambda, then E equals hc per lambda, which means we don't have to be given a frequency to work these problems. We can start out with a wavelength, and you can do a two-step problem where you first use the wavelength to determine the frequency using lambda nu equals celeritas like we did previously, or you can use this derived equation that energy equals hc per lambda, and that's what we're going to do right now. So let's take a look at this problem. It asks what amount of energy is associated. So what amount of energy, meant to do that in red, sorry, energy is associated with a beam of light that has a wavelength of 656.28 nanometers. So again, energy is the question. Lambda is given to us as 656.28 nanometers, which means we are going to have to convert to meters. But we can do that easily by recalling that 1 meter per every 1 times 10 to the 9th nanometers. When you do that, you should get 6.5628 times 10 to the negative 7th meters. And the equation that I'm going to want to use is E equals hc per lambda. So when I substitute in, h is my constant of 6.626 times 10 to the negative 34th joule seconds. C, celeritas, is that speed of light, 3.00 times 10 to the 8th meters per second. And then wavelength of 6.5628 times 10 to the negative 7th meters. Looking ahead to units, notice meters in the numerator cancel meters in the denominator. Seconds in the numerator cancel seconds in the denominator. And I'm going to be left with just the units of joules, like I would expect. So now when you substitute all this into your calculator and you solve it out, you should get an answer of 3.029 times 10 to the negative 19th, and as I've already pointed out, units of joules. So we've looked at how to calculate energy when you start with frequency, and now how to calculate energy if you start out with wavelength. And again, you could do this as a two-step problem where you first take, again, the idea that lambda nu equals c, rearrange that for nu, c per lambda, calculate your frequency, and then use E equals h nu, where you would substitute in. So you can, again, do this as a two-step problem, but it is a little bit easier to do it all at once if you know how to program this into your calculator properly, which warrants this. If you're going to use these exponents like I've written it out, times 10 to the negative 34th, rather than using the exponential key on your calculator, please make sure that you put these values inside of their parentheses. Just like what I've written out, open parentheses, the numerical value, close parentheses, open parentheses, the numerical value, close parentheses. And then I hit enter at this point, and then divide by open parentheses, my wavelength, close parentheses, and then hit enter a second time. Okay, it's going to save you from making some type of calculator error. Okay, so last little thing on this before I close out, there are two other arrangements for the energy equation. First, starting out with E equals h nu. If you're given the energy and asked for the frequency, this can be rearranged by dividing both sides by Planck's constant to get that frequency equals energy divided by Planck's constant. Likewise, if they start you out with energy and ask for a wavelength, you can start with E equals hc per lambda and rearrange by multiplying both sides by lambda and then dividing both sides by energy to get the final equation that lambda equals hc per E. Right? So those are two other derivations that can be made from those energy equations. So hopefully all this has made sense to you. If not, then leave me your questions in the comments. I'll get back to you as soon as possible. Also, if you've got ideas for future videos, let me know about those by leaving those in the comments as well. Okay. Also, reminder to you, go on and subscribe to this channel. That way you'll be notified whenever I upload new videos. Okay. Thanks. Take care.